Countdown.
Tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi YouTuber Malaysia, sebuah inisiatif e-didik Malaysia dan Kelab Guru Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Teachers, parents, and all the wonderful students. Welcome to Pusat Academy YouTuber. Bermula percuma, selamanya percuma. How are you doing today? I hope all of you ready for today's lesson. Before we proceed, let's begin our section by reciting a prayer for Muslim. The Muslim may pray according to your own religions. Okay, let me introduce myself. I'm Teacher Kong from College Matrikulasi Perak, the moderator of today. We at Pusat Tuisyen Academy YouTuber will provide you with free online classes. Let's take this opportunity to do your revision. So, are you ready? Let me introduce our teacher for today's lesson. We have Teacher Tang from College Matrikulasi Selangor. You are now live on Teacher Tang's channel. Please support her channel by clicking subscribe now. Okay, the topic of today's lesson is periodicity. And together with us, we also have Cikgu Mawa, who is control host, in charge ensure the smoothness of our lesson on technical support. So before we begin, I have a few reminders to all of you. First, please pay attention to our lesson. Stop chatting and use the chat section wisely. Number two, regarding certificate link, the link will be given at the end of our section. But from time to time, please pay attention. We will give you the code of this section. Please use e-didik account when you fill in your particulars and make sure to listen to the passcode given by the presenter. So without further ado, let's welcome Teacher Tang.
College Matrikulasi Selangor. So I have 8 years of experience teaching chemistry. This is my team. So Kimia Prayu. So these are my teammates. So we are led by Cikgu Shannon. So my teammates consist of Teacher Vivi Lau, me, Cikgu Shannon, Cikgu Mawa, and Teacher Kong. So we all made a collections of the PDPC video for chemistry, so you all can have a look on the video collections if you want to find more PDPC videos for chemistry pre-U. So this is the pre-U group for mathematics, so led by Teacher Yin. So for the biology pre-U, led by Cikgu Faiza. And then for the physics group, led by Cikgu Teacher Yi. And then for the accounts and economics group, so these are the members led by Cikgu Yati. And then come to my topics for today. So is periodicity part 3. So remember, periodicity started with Cikgu Shannon on atomic and also ionic radii. And then last week, Teacher Vivi, she covered the oxide of period 3 and also the metallic properties. So today I will continue with the ionization's energy for period 2 and period 3 elements. So before that, we need to look at the definitions of ionization's energy. So what is first ionization's energy? First ionization's energy refer to the minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of unipositive charge gaseous ion. So what does it mean? So basically it means that, for example, if we have magnesium atom, so magnesium atom in the gaseous state. So first ionization's energy refer to energy that is required to remove 1 mole of electron from this 1 mole of magnesium gaseous atoms. So after remove 1 mole of electron, so we get 1 mole of unipositive charge gaseous magnesium ion, and the energy required to perform this is what we call as first ionization's energy, or we can also write it as this. So this is the first ionization's energy.
Hi, teacher.
And then what is second ionization energy? Yeah. Oh, the first class code. So the first class code is 8. 8. Okay, so the first class code is 8. So for second ionization's energy, the minimum is the minimum energy required to remove 1 mole of electrons from 1 mole of unipositive charge gaseous ion to form 1 mole of positive 2 charged gaseous ions. So what does it mean? So we know that after first ionization's energy, we get magnesium ion, positive 1. So in second ionization's energy, we start with magnesium positive 1 gaseous ion. Then we remove another mole of electrons. As another mole of electron is being removed from this magnesium positive 1 ion, then it becomes magnesium 2 plus gaseous ion. And the energy involved to remove this 1 mole of electron from this positive 1 magnesium ion is what we call as the second ionization's energy for magnesium. Okay, so this is the definition for our topics today. So for ionization's energy, so last week, teacher Vivi Lau already covered metallic characteristic. So for metals, usually they will have lower ionization's energy. Why? It is because, remember, metal tend to donate electrons. Okay, so tend to donate electrons. So metallic characteristic means that how easy they donate electrons. So if metal easy to donate electron means that they will have lower ionization's energy, or in other words, less energy is needed to remove 1 mole of electron from metal atoms. So now we move on to look at question 1. Okay, so which of the following is the chemical equation to represent the third ionization's energy of magnesium? So just now I already covered the first and the second ionization's energy of magnesium. So now in this question, so what do you think is the equation for the third ionization's energy of magnesium? So any answer from the students? Yeah, moderator?
There's
not
no
yet.
answer yet.
Oh, no answer yet. Okay, so...
Okay, teacher Titi, there is one student from Justine Chai answer B.
Okay, B. Very good. It's B. Okay, so why? Remember, after second ionization's energy, we form Mg2+, okay, in the gaseous state. So for the third ionization's energy, means that after we get the positive 2 magnesium ion, we want to remove another mole of electron. So after we remove another mole of electron, then we will get Mg3+ in the gaseous state. Okay, and energy involved in removing this 1 mole of electron is what we call as the third ionization's energy for magnesium. Okay, very good. The answer is B. So now we move on to look at factors affecting ionization's energy. So basically, for ionization's energy, we look at how easy is the electron to be removed from the atom or ion. Okay, and how easy this electron is being removed from the atom or ion, it depends on the attractive forces of the nucleus on the valence or remaining electrons. Remember, in the atom, inside the nucleus having the positive charge. And this positive charge, okay, let me draw first. Okay, so this positive charge, okay, so basically will attract the electron. Okay, let me draw this. Like for example, magnesium. Okay, magnesium. So in the nucleus consists of positive charge, and this positive charge will attract the electron. Okay, will attract the electron. Okay, and how easy the electron is being removed from the atom, it depends on the strength of this positive charge on the nucleus on the valence electron. Okay, and the second factor affecting how easily an electron is being removed is the screening effect. Okay, so still remember, okay, so like for example, this is the valence electron. So this valence electron experiences attractive forces by the nucleus, and at the same time, it is also experiencing the repulsion from the inner shell electron. And this repulsion from the inner shell electron is what we call a screening effect. And basically, these two effects is going to affect how easily an atom or ion, how easily an electron is being removed from the atom or ions. Okay, and therefore, first ionization's energy of an element is being influenced by the effective nuclear charge, screening effect, and also the atomic size. So Cikgu Shana already covered the atomic size basically is depending on these two factors. Okay, therefore, for the first ionization's energy, besides depending on these two factors, it is also affected by the atomic size. So now we shall look at period 3. So across period 3, from sodium to argon, okay, we know that in the nucleus, the proton number increases from sodium to argon. So means that from sodium to argon, it becomes more positively charged in the nucleus. Okay, in the nucleus, it becomes more positively charged. Okay, the attractive forces of the nucleus on the valence electrons become stronger because the proton number increases as across period 3. Then how about the screening effect? Remember, the screening effect is determined by the inner shell's electron. So from sodium to argon, can you see that these are the inner shell's electron? Can you see that the number of inner shell's electron are the same? So means that the screening effect or shielding effect stays almost the same as across the period 3. Again, although the proton number increases, but the number of inner shell's electron remain the same, so causes the screening effect to stay almost constant as across period 3. So this causes the effective nuclear charge. So what is effective nuclear charge? So effective nuclear charge basically is referring to what is the net positive charge experienced by the, okay, let me return to this picture that I drew just now. Okay. So magnesium, I use magnesium as example. Okay, so basically this valence electron experience attractive forces by the nucleus, and it is also shielded or screened by the inner shell's electron. So what is the positive charge or attractive forces, net attractive forces that experienced by this valence electrons is what we call as effective nuclear charge. Okay, so the net attractive forces experienced by the valence shell's electron is what we call as effective nuclear charge. So across the period 3, proton numbers increases, the screening effect stays almost constant. This causes the effective nuclear charge to increase as across period 3. So this will cause, so we are going to see how this is going to affect the first ionization's energy of the elements across the period. So basically, so we know that from the period 3 just now, we know that as across the period, proton number increases. So means that now the nuclear charge in the nucleus increases as across the period. Okay. However, the screening effect stays almost the same because the number of inner shell's electrons stays the same. So this will result in increase in effective nuclear charge as across the period. So this then will cause the attractions of the nucleus on the valence electrons become stronger as across the period. So means that the attractive forces by the nucleus on the valence electron become stronger as across the period, and this causes the distance between the nucleus and the outermost shell's electrons become closer as across the period, and this causes the atomic radii to decrease as across the period. Okay, and this had already been discussed by Cikgu Shannon. Okay, and then therefore, as the size becomes smaller, means that now the energy needed to remove 1 mole of electrons increases as across the period and causes first ionization's energy to increase as across the period. This applies for both period 3 and also period 2. So then how about as going down a group? So I give you examples, group 1. So as going down group 1, can you see that? So for lithium, this is inner shell's electron. For sodium, this is the inner shell's electron. And for potassium, this is the inner shell's electron. So can you see that as going down the group, the inner shell's electrons increases, okay? Because the number of inner shells filled with electrons increases. So what does this imply? So basically it means that as the number of inner shells filled with electrons increases, it implies that the screening effect increases as going down the group. Okay, and for going down the group, basically the screening effect will be the dominating factor in affecting the first ionization's energy of the elements. So now shall we look at the variations of first ionization's energy going down the group. So I told you already, when going down the group, screening effect is the dominating factor. So why? It is because, when going down the group, we can see that the number of shells filled with electrons for each element increases. This causes the screening effect to increase in greater amount compared to increase in nuclear charge. Okay, so because of that, now the attractions of the nucleus on the outermost electrons become weaker. Okay, so these outermost electrons basically refer to the valence electron. So we know that going down the group, the dominating factor is the screening effect. Screening effect causes the valence electron to have weaker attractions by the nucleus. Okay, so means that now the valence electron will be further away from the nucleus, and this causes the atomic radii to increase as going down the group. So as the atomic radii become bigger, so means that now we need less energy to remove 1 mole of electron from an atom. Okay, therefore, as going down group 1, the first ionization's energy of element decreases. So this is the general trend for first ionization's energy for elements going down a group. So now we move on to look at question number 2. So in order to do this question, we must always ask ourselves whether it is going down the group or across a period. Like for example, in this question, so lithium, oxygen, and fluorine. So this is going down the group or across a period. So I give you the proton number. Lithium is 3, oxygen is 8, and fluorine is 9. So there's a hint. So you just need to know whether it is across the period. Across the period means that same period. Going down the group means that same group. So any student attempt?
Hi, Teacher Tang.
Yeah.
Answer from Peru, A.
A. Okay, so
Justine
shall we
also the
have
same.
a look?
Answer is A.
Okay, so shall we have a look on the answer? Okay, so this is increasing order. Increasing order means that the smallest to the biggest, right? Okay, energy, first ionization's energy. Okay, so shall we have a look? Okay, so lithium. Okay, so remember lithium, this is across a period because this is period 2. So lithium, from lithium to fluorine, proton number increases. Okay, so proton number increases. So this will cause the effective nuclear charge to increase. So will cause the attractions to become stronger. So distance between nucleus and the valence electron become smaller. So size becomes smaller, so means that it will become harder to remove electrons as across the period. So means that the energy required will become bigger. Okay, so therefore your answer A is correct. Very good. Well done, students. So now we move on to look at question number 3. So
Hi, Teacher
descending order. Yeah.
What is the number, the second number for the codes?
Okay, so the second class code is 0. Okay, so the second class code is 0. Okay, the second class code is 0. Okay, so now you can attempt question number 3. So arrange the following elements in descending order of first ionization's energy. So now this is, okay, any answer? Any answer from the students?
Not yet. Okay,
Okay.
wait for a while. Maybe can give some hints to them.
Okay, so this is group 17 elements. So group 17 elements, so they belong to the same group. So means that this is going down the group.
Oh, Teacher Tang, there's an answer from Peru. There's an answer from Peru, B.
Yeah. Okay, good. The answer is B. So remember, going down the group, okay, so going down the group, the dominating factor is the screening effect because the number of inner shells filled with electrons increases. Okay, so this will cause the attractions of the nucleus on the valence electrons become weaker. So distance further, atomic size increases, so less energy needed to remove the one more of electrons. Okay, so therefore is B, the answer. Very good. So now we move on to look at variations in the first ionization's energy across period 2 and period 3. So can you see that generally across period 2 and period 3, the first ionization's energy is in outward trends. So means that generally from lithium to neon, the first ionization's energy increases. So as from sodium to argon, the first ionization's energy generally increases. However, if we look at the there are dips between group 2 and group 13. Oh, sorry. Oops. So there's a dip between group 2 and group 13. So for both period, and also between, so this is group 2 and this is group 13. So this is group 2 and this is group 13 as well. And then also there's another dip between group 15 and group 16 for both period 3 and period 2. So why? Okay, so we look at why there's a dip between group 2 and group 13. So supposedly we will expect across the period, so boron has higher proton number, right? So therefore it should have higher effective nuclear charge. So smaller size, supposedly the first ionization's energy should be higher than beryllium, so as aluminum. However, we can see that for period 2, beryllium has higher first ionization's energy than boron, and the same trend goes for period 3, where magnesium group 2 element has higher first ionization's energy than aluminum. So why? So beryllium has higher first ionization's energy than boron because if we write out the electronic configuration for beryllium, we can see that the electrons are filling the 2s orbital fully. Okay, so or in other words, we can say for beryllium, the 2s orbital is fully filled. Okay, 2s orbital is fully filled. While for boron, the last electron go to 2p subshell, and there is only one electron in the 2p subshell, which causes the 2p subshell to be partially filled. So remember, 2s subshell, 2s orbital, only one orbital, so can only accommodate 2 electrons. So this is fully filled. But for 2p subshell consists of 3 orbitals, so maximum can fill 6 electrons. But here in boron, only been filled with 1 electron. So we call this subshell be partially filled. While for the 2s subshell, this is fully filled. So basically, for the subshell that is fully filled, it is more stable. You must remember this. Okay, so fully filled subshell, it is more stable compared to partially filled subshell. So 2s orbital, which is fully filled, therefore it is more stable compared to the 2p subshell, which is partially filled in boron. Okay, because of that, we need more energy to remove 1 electron from more stable fully filled 2s subshell of beryllium compared to remove 1 electron from less stable partially filled 2p subshell of boron. Okay, or we can also look in another way. So remember, we are talking about ionization's energy. So ionization's energy means that we want to remove electron. So you know that, okay, let me draw quickly. So remove electron, basically, we want to move the electron to the infinity. We want to move the electron to the infinity. Okay, so we look at boron. Okay, so boron, so it's like this. Okay, this is boron. While beryllium, it is like this. Okay, so for boron, we want to move this electron to infinity. Okay, while for beryllium, we are removing this electron to infinity, 1 electron. Okay, I can rub this off. Okay, it's okay. So 1 electron to infinity. So can you see that based on the diagram that I draw, can you see that we require less energy to remove the electron from the 2p subshell of boron compared to 2s subshell of beryllium. So why? Because 2p subshell in boron is located at higher energy level. So when it is located at higher energy level, it is more well shielded, okay, by the inner electron compared to the 2s subshell. Okay, therefore, less energy is needed to remove 1 electron from the partially filled 2p subshell of boron compared to remove an electron from the 2s subshell of beryllium. Okay, so the same pattern goes to magnesium and aluminium in period 3. Okay, and same explanations as well. So,
Hi, Teacher Tang.
Yeah?
Let's stop for a while for advertisement. Thank you.
Okay.
Alah, apa ni? PKPB lagi. SPM pula ditangguhkan. Jenuhlah nak bayar yuran tuition. Pernah dengar tentang tuition percuma? Kami di Akademi YouTuber menyediakan tuition online secara percuma kepada anda semua. Ada prasekolah, sekolah rendah, sekolah menengah, STPM, juga untuk matrikulasi. Percuma je. Jom layari laman sesawang www.academyyoutuber.com.
Okay, let's continue today's lesson with Teacher Tang.
Welcome back. Okay, so beside between group 2 and group 13, so there's another dip between group 15 and group 16. So why? Okay, so I use period 2, nitrogen and oxygen as the example. So if we write out the electronic configurations for nitrogen, so this is the electronic configurations for nitrogen. So while this is the electronic configurations for oxygen. So based on the electronic configuration, we can see that, so in nitrogen, the 2p subshell is half filled. Remember, 2p subshell fully filled would be 6 electrons. In nitrogen, the 2p subshell is filled with 3 electrons. Okay, so it is half filled. And this half filled subshell basically is more stable. Okay, so while for oxygen, it is partially filled because there are 4 electrons inside the 2p subshell. So this is partially filled. Remember, partially filled, less stable. So because of that, so easier to remove 1 electron from oxygen compared to nitrogen. So we will expect nitrogen atom to have higher first ionization energy compared to oxygen atom, because in nitrogen we are removing the electron from the more stable half filled 2p subshell. Okay, so more energy required, okay, to remove an electron from more stable half filled 2p subshell of nitrogen. So beside that, we can also see in the way that for the 2p subshell of oxygen, can you see that in one of the orbitals, the oxygen having the electrons pairing out in one of the 2p orbitals. And this electron pairing out basically increase the electrostatic repulsion. So refer to electron-electron repulsion between these 2 electrons. Okay, and this electron repulsion make it less stable. So when it is less stable, so means that less energy is needed to remove an electron from the 2p subshell of oxygen. So the same trend goes for period 3 between phosphorus and sulfur, and then same explanations can be applied. Okay, we need to write out the electronic configuration, then only we can explain, okay, whether it's half filled or partially filled. Half filled or fully filled, more stable than the partially filled. So when more stable, more energy is required to remove an electron from the atom. Will cause the first ionization's energy to be higher. So now we move on to look at the successive ionization's energies. Okay, so in general, so shall we look at the sodium first? Can you see that for sodium, successive ionization's energy increases? Okay, magnesium as well, aluminum as well. Okay, the successive ionization's energy for an element basically increases. Okay, so why? It is because successive ionization's energy, so basically means that an atom will continuously remove the electrons. Okay, while the proton number, the number of proton is still remain the same. Okay, it's from an atom, for example, magnesium. So magnesium just now. Okay. So what is successive ionization's energy? Successive ionization's energy basically refer to we continuously remove electron. Like for example, we remove this is the first, second, third, fourth, until all the electrons be removed from that atom. Okay. So basically, successive ionization's energy of an element increases means that first electron, we use less energy compared to the second electron. And third electron, we need more energy to remove it compared to the second, and so on. Okay, so why? It is because as we continuously remove electron, the number of proton inside the nucleus is still the same. So means that now the remaining electrons will experience greater attractive forces by the nucleus because less electrons already. Okay, so and the remaining electron basically will be closer to the nucleus. Therefore, more energy is needed to remove the next electron. Or in generally, we can also say that the successive ionization's energy of an element increases because more energy is required to remove the electron from an increasingly positive charged ions. Okay? So if we are being given successive ionization's energies of an element, what are the informations that we can extract from it? Okay? So basically, from the successive ionization's energy of an element, we can deduce the positions of the element in the periodic table. Okay, so how to do that? First, we need to plot the log to the base of 10 ionization's energy versus number of electrons removed graph. Okay, and then from the graph, we can group the electrons into their respective energy levels. Okay, and this will tells us the period. Okay, so how many energy levels is going to tell us how many shells filled with electrons, and that will tells us how that particular element is belongs to which period in the periodic table. Okay, and then we can also determine the number of valence electron, and then write the electronic configuration, and also determine the group of the element in the periodic table. Okay, so like for example, so based on the successive ionization's energy of sodium just now, so this is the graph that we need to plot. So log to the base of 10 ionization's energy versus the number of electrons removed. Remember sodium, okay? So, and then from that, we need to determine the energy level. Remember, I told you already, the number of energy levels is going to tell us the period. So can you see that from this graph, there are 3 levels of energy. 3 levels of energy. Yeah? Oh,
Let's
the
announce the
third class code. Okay, so the third class code is 2. Okay, the third class code is 2. So the third class code is 2. Okay, so from the graph, we can see that there are 3 energy levels. So means that there are 3 shells filled with electron. So which one is energy level 1, n equals to 1? Which one is n equals to 2? Which one is n equals to 3? Okay, so how to know? Okay, so we need to know that, you see, if so now we are having sodium, right? So we are having sodium. So based on here, we have 3 energy levels. So can you see that? Okay, so can you see that valence electron? So valence electron is furthest away from the nucleus. So if furthest away from the nucleus, easiest to remove, means that the first ionization's energy should be the lowest. So where in the graph that is the lowest energy? Here. Okay, so means that this one must be the furthest away from the nucleus, and therefore this should be N3, the third energy level. I think something wrong today with my... Okay, so this is n equals to 3. Okay, so n equals to 3. So, and if this is n equals to 3 furthest away from the nucleus, okay, so easiest to remove the electron. Okay, and this must be n equals to 2, and therefore this must be n equals to 1. Okay, so we have, from the graph, we know how many energy levels. So how many shell filled with electron? So 3 energy levels. So 3 shells filled with electron, and the lowest, it must be the furthest from the nucleus. Okay, and then from here we can see that at n equals to 3, will only consist of 1 electron. Okay, so okay, I will continue. Okay, so only consists of 1 electron. So this is our n equals to 3 just now. So this is the first electron that is being removed. Okay, and then between the first electron and the second electron, can you see that there is a large difference in ionization's energy? So means that started from the second electron. Okay, so this is one group, right? Just now n equals to 2. So started from the second electron, we start to remove the electron from another energy level. So after a large difference, the next electron is being removed from another energy level, or in other words, is removed from another inner shell. Okay, another inner shell. Okay, so therefore, if second electron started to be removed from another energy level, means that at n equals to 3, our outermost shell only consists of 1 electron. Okay, n equals to 3 only consists of 1 electron, only have 1 valence electron in the valence shell. Okay, so and then, so between the second electron to the 9th electron, so this is 1 energy level, n equals to 2. Can you see that now the successive electron, okay, so the energy required to remove the successive electron increase at almost constant rate. Okay, so not much. Okay, so means that from the second to the 9th electron, they are being removed from the same shell. Or same energy level. Therefore, not much difference, not much increase in energy required to remove the next electron. Okay, and between second to the 9th electron, there are 8 electrons. So means that at energy level n equals to 2, it consists of 8 electrons. Then now we move on. So just now, this is the 9th electron. So means that this is the 10th electron. Okay, so between the 9th and the 10th electron, can you see that there is another large difference. There's another large difference in ionization energy. Okay, so means that start from the 10th electron, it is being removed from another energy level, another inner shell. Okay, so and this is our n equals to 1 just now. Okay, so n equals to 1. Okay, so consists of 2 electrons. Okay, so why 2 electrons? It is because between the 10 and the 11 electron, can you see that the energy required to remove the successive electron is only increased at almost constant rate, not much increase in energy required to remove the 11 electron compared to the 10 electron that is being removed. Okay, so because of that, in n equals to 1 consists of 2 electrons. So with the energy levels information, then we can come to a conclusion to deduce the positions of the element in the periodic table, and also to write the electronic configuration for the elements. Okay, so remember the first, the n equals to 1, have 2 electrons. So this is n equals to 1, this is n equals to 2, and this is n equals to 3. Okay, so, and then can you see that in our outermost shell consists of 1 electron. So means that this element consists of 1 valence electron. So if consists of 1 valence electron, means that it must be group 1 element. It must be a group 1 element. Okay, so, and then remember, so if 1 valence electron, okay, it must be S block. It must be S block, and then it has 3 shell filled with electron, 3 energy level, 3 shell filled with electron. Therefore, the valence electronic configuration is 3s1. So this is from the from this 3 shells filled with electron, and 1 valence electron, so S block, and then S1, 3s1. And how to write the electronic configuration? So basically, we start with 1s2, 2s2 until 3s1 to get the complete electronic configurations for the element. Okay, so this is how we use successive ionizations energy using the graphical method to determine the positions of the element in the periodic table. So sometimes they don't give us the full set of successive ionizations energy. So if we are not being given full set of successive ionizations energy, then how do we deduce the positions of the element in the periodic table? So they are still aware, so we can find the difference in successive ionizations energy. Like for example, if we are only being given 4 successive ionizations energy data, then how do we know this element is belong to which group in the periodic table? Okay, so definitely we can't determine the period because we do not know total it has how many energy levels, so we can't determine the period. If we don't get the full set of successive ionizations energy data, we can only determine the group. Okay, and then write the valence electronic configuration. We can't determine the period. Okay, so how to determine the group for this element? So basically, we can find the large difference. So remember just now, we need to find the large difference in order to know the electron, which is the next electron that is being removed from the inner shell. So how to find the large difference? So basically, we can use the next ionizations energy minus the previous one. So I2 minus I1. So, and then the next one minus the previous one, I3 minus I2. And then the fourth ionization's energy minus the previous one, the third ionization's energy. And then from there, can you see that this is the largest difference? So this is the largest difference. So between the third and also the fourth ionization's energy. So what does this imply? So now the largest difference is between the third electron and also the fourth electron. So means that I need to write the fourth electron and the third electron. So means that start from the fourth electron, we are removing it from the inner shell. Okay, so means that the electrons before is being removed from the outermost shell or valence shell. Because the fourth electron started to remove from the inner shell. That's why the large difference occurs between the fourth when remove the fourth electrons and from the third electrons. Okay. So how do we explain this? So from the large difference, from the difference of in ionization's energy, we can see that the large difference is between the third and the fourth ionization's energy. So therefore, the fourth electron is removed from the inner shell, and we can conclude that therefore the elements have 3 valence electrons. So if it has 3 valence electrons, means that it must be from the p block. Okay, it must be from the p block. So this is therefore the valence electronic configuration. I put it N here because we do not know the period. We do not know the total number of shells filled with electrons that particular element has. So because of that, we don't know our N. So I will just leave it as the N, okay, highest N. So, and then it must be from the p block element, and it must belong to the group 13 because 3 valence electrons. Okay, now we move on to question number 4. So from this graph, so this is the graphical method. So they give you the full set of successive ionizations energy data. So could you determine the positions of the element in the periodic table? So remember, I told you already, we need to determine the energy levels. So energy levels. So how many energy levels do we have? Okay, for question number 4.1, how many energy levels do we have? Any students? Based on the graph, how many energy levels do we have? Any students giving answer?
Okay, no yet.
Yeah. Okay, very obvious from the graph. Okay. So there are two energy levels.
Student answer. There are 2 student answer.
Yeah.
Huiru and Jizin answer 2.
Okay, good, very good. So which one? Okay, so let me put A and B. So which one is n equals to 2, A or B? So there are 2, so the highest n must be n equals to 2. So which one, A or B, is n equals to 2? Which energy level is n equals to 2?
Okay, Huiru and Jizin answer A.
Okay, good. So A is n equals to 2. So this is A. So n equals to 1, that is our B. So can you see that A consists of 1, 2, 3, 4, so 4 electrons. So B consists of 2. Okay, so from here, can you tell me how many valence electrons electron does these elements have? Yeah, student, how many valence electron does this element have? Nobody answer?
Answer from Puelu, 4.
Very good. 4. So if 4 means that this element belong to group belongs to group. So remember, the topic for today is only period 2 and period 3. So period 2 and period 3 elements only having S block and P block. So if having four valence electron, this belongs to which group?
Puelu answer P.
Yeah, P block. So group what? Which group? So it must be group 14. Okay, so group 14. Okay, so now anybody want to tell me, so total there are 2 energy levels. So total 2 energy levels, this implies that it has how many shells filled with electron? So implies that how many shells filled with electrons? So this element has how many electron shells? I should say shells filled with electron. 2 energy levels. Total 2, so means that it will be 2 shells filled with electron. Okay, so therefore, if we want to write the valence electronic configuration, it will be, so 4 valence electron, so 2 shell filled with electrons, so it will be 2s2, 2p2. Okay, so if we want to write the electronic configuration, then we need to start with 1s2, 2s2, 2p2. So this is how we do question number 4. Okay, so now we move on to look at the question number 5.
Teacher Tang, before moving to question number 5, let's announce the class code number 4, the 4th class code.
Oh, the 4th class code is 3. The 4th class code is 3. So the 4th class code is 3. Okay, so this question very easy because I already calculated the energy difference for you. So where is the largest difference? So can you see that the largest difference is between which ionization energies? So very obvious, it is between the second and the third ionization energy. So the largest difference is between the second and the third electrons being removed. Okay, so what does it mean? So it means that the third electron we started to remove from the inner shell. So based on this, so students, can you tell me how many valence electron does element M have? So this element M has how many valence electron? Any answer from the students? How many valence electron does this element M have? No answer?
No answer yet.
Oh, no answer yet. Remember, here is the
Okay, there are two
largest
student
difference
answer.
in ionization's
two.
energy. So, yeah.
Pairu answer 2, Jessie answer 2.
Okay, very good. So valence electron. Very good, very good. So there are two valence electrons because third electron we started to remove from the inner shell. So means that the first and the second electron are be removed from the outermost shell. Okay, therefore there are two valence electron. So if two valence electron means that element N belongs to which group in the periodic table? Any answer from the students? The group for element M. Two valence electron belongs to which group in the periodic table?
Pairu answer 2.
Very good, very good. So group 2. Okay. That I made. For the successive ionization's energy, if you are not being given the full set, actually there is another way whereby you can use the ratio to determine the largest difference between ionization's energy and to determine how many valence electron. So that is in this video. So if you want to use that method, you can refer to the successive ionization's energies video to know the calculations details. Okay. So basically that's it from me. So thank you, class. Thank you, students. Okay. So back to our moderator.
Okay, thank you, teacher. Today's lesson. We have learned a lot from teacher Tang about periodicity. Congratulations to those who are able to follow our section from the beginning till the end. And thank you very much, teacher Tang. Okay, and before I provide the certificate link, right, please off the live chat button and click subscribe button if you haven't. This is to show your appreciation to teacher Tang for giving you a free lesson. Don't forget to click the bell button too, so you won't miss out any new video and live classes from teacher Tang. If you liked today's class, then please click like and share it to your social media friends. Let's share the knowledge you received today with them. Sharing is caring, right? When you have finished, type done in the chat section. Okay, about the class code, right? Just now there are 4 class codes, okay, were given by teacher Tang. So this is you have to join 4 class codes as the password, okay? Something like password. Then you have to key in for the third link. Once again, I would like for this interesting lesson. Thank you also to teacher Marwa for being with us today. Please.
Tuisyen online percuma. Tuisyen online percuma. Layari www.academyyoutuber bagi mengikuti tuisyen online secara percuma. Prasekolah, sekolah rendah, sekolah menengah, semua ada di Akademi YouTuber. Rujuk jadual di laman sesawang www.academyyoutuber.com. Semoga masa terluang anak-anak anda diisi dengan sebaiknya. Tuisyen online percuma, mestilah Akademi YouTuber.
Dibawakan kepada anda oleh Akademi YouTuber.